level you are, the best comfort level, right? So, and cannot be like, you are on the other side. I don't know what is going on. And the thing is, I would not like to just call from here randomly and say, okay, you say. Right? So, if you come out voluntarily, it will be good. So, but it is nice that. Right? And how many are you from out of Gujarat students? I mean, right now you are all from home. But in the chat box, just tell me how many of you are out of Gujarat? So very few, right? So anybody, it was by mistake or somebody raised the hand? Open queue, what is this? Okay, so all these raised hands are out of Gujarat. Many students. So it was by mistake or you raised the hand, right? Okay, okay. And others are from here. So no problem. Just I wanted to know that in this condition, because of those who are out of Gujarat, it is good. And anyway, so anybody in campus or all from home only? Let me clear this queue. Lower all. No, I mean, just raise the hand. How many in campus? Anybody? No, no. Oh. Well, you have to be at home. I think things will be fine soon. Okay. Okay, no problem. So analog circuit, what do you mean by analog circuit? You can unmute your mic, okay? Please unmute your mic and you can answer. If you answer, you leave your ID in the chat box. What do you mean by analog circuit? And if this is the name, then what is another, another kind of circuits? How many of circuits are there? This is analog. Is there other kind? Hello? Do you think I should give the say up the name and you want to answer? Chirag, unmute your mic, please.
Yes, ma'am.
Yes, very good, Chirag. So tell me, this. What do you mean by analog circuits?
Good morning, ma'am. Analog
Yes,
circuit. What I understand by that, like
yes.
circuit having currents, having a default, like having values like in point values, not in distinct digital value, one and zeros like that. And we can get voltage like a 3.7 or many things like that. That variable that is not like a pulse is not pulse like the graph.
It's not 0 and 1. The voltage and current can have any value. That's what you mean, right?
Yes, we can like in digital. What we understand that we have like range. Like if we get voltage between 5 and 0, then we can say that it is 1, or like 0 to -5, then we can say that it is 0.
But as far as circuits are concerned, where are these analog circuits used? Any idea? These are
Uh,
circuits, right?
Analog circuits like it is used in many things like in this IoT things like transferring data and then just demoduling and moduling things like communication
Mhm.
systems anywhere.
Okay. Okay, good, Chirag. Anybody would like to add to what Chirag said? See, you are here to learn. Anything wrong is also welcome. But I will motivate you to speak out because, tomorrow you will be BTech, you will be working somewhere. I want you to be manager, right? You cannot be, you have to be a leader. You cannot be quiet. So from the very first day, I'm just Darshan. Please help Chirag. Darshan, where is he? So to Darshan Popat, please unmute your mic. See, if you are not there, the other side, it is a crime, huh? This is not the way. Even I can do that. I'll be here showing online and then I will just go away. Will that be okay? See, this is something ridiculous because this is not allowed. How come you be not there? You are showing here. Then don't email me or message me that you are
Hello,
sorry.
ma'am.
Who is this?
Yeah, it's me, Darshan.
Why do you take so much of time?
Sorry, my mic was not unmuted.
Unmute your mic. You should not take so much of time. Be ready, okay, mentally, everybody.
Yes, yes, ma'am.
Yes, please help Chirag Darshan.
Yes, ma'am. Sorry, what was the question?
Did you listen to Chirag?
No, ma'am.
Then why? See, so you want us to spend time in just figuring out that why didn't you answer him and the whole lecture?
Sorry, ma'am.
No, no, that's what. Don't tell me sorry or don't email me, but I am going to at least note down every time, okay? Then who is this Gandhi Somin? Please help Chirag.
Yes, ma'am. As per Chirag said that analog circuits are used in
So
communication
you add
systems.
something more, okay? Somin, what
Yes,
Chirag
ma'am.
said in that line, you add something more if you can.
Uh, can you repeat, ma'am? I didn't listen.
See, my question was, what do you mean by analog circuit? Just the name of the course. You have studied now, you are in second year, fourth
Yes, ma'am.
semester. थोड़ा आइडिया होगा तो बताओ एनालॉग क्या होता है.
Yes, ma'am. Analog circuits are usually which can give input, take input or output analog values like continuous, not discrete as digital values.
No, no, so don't repeat. So you know the same thing. You nothing more. What Chirag said. Anybody would like to say?
Good morning, ma'am.
Okay. Yes, please. हाँ बोलो.
Yes, ma'am. Good morning, ma'am. Ma'am, I would like to, miss, as per I understand, an analog circuit is a circuit which
Please tell me
involves
your name, please.
analog signals.
नहीं, that is fine. Analog circuit है तो analog signal होगा. But analog circuit क्या है? The circuit that will process analog signal. But what are those circuits? Where are they used? What is the significance of this? Why analog? Not just circuit, right? Anyway, so no problem. I just wanted to know how well you are. So, okay. So let me see now, be attentive, okay? Because you should know why you are doing analog circuit. Okay, and the significance of this term. So I am talking to you in a broader sense. So this electronics, it is the circuits that we are using, the electronics in general, the circuits, all electronics. That is more than half a century, right? We are using these electronic circuits. And it has evolved by time. Okay, now the circuits are basically, they process signal, and the signals, they carry information, right? That information can be any parameter, okay? And let's say that you want to measure pressure, right? So that pressure or that temperature in circuits, when you see some quantity, right? So that pressure or that temperature in electronics, we have your main parameters are current and voltage, okay? In other than that, so this current and voltage is an output of the change in the resistance. You are applying some voltage, the R is changing, or in some cases capacitance. So all these sensors. So if I talk of a simple this thing, let's say a sensor, okay, a temperature sensor, right? Then by the temperature, R will change. By changing R, current will change, right? And if you measure that current, you can know the temperature, for example. Okay, so all of this, whatever the quantity that you are measuring in electronics, it will come down to current and voltage. Okay, now any quantity when any parameter, temperature, or you are measuring pressure, right? So corresponding to the pressure, right? So depending on the physics of that sensor, R will change or capacitance will change, and that's how voltage or current will change. Okay, and we are measuring that. So it's a game of current and voltage at the end of the day, which is output of the change of R or C or voltage. And this current and voltage, when they are generated, right, they are analog. They can be from some milliampere to, right, microampere to milli to some amperes, depends on the circuit or the sensor or how it is generated. So basically it is carrying information. Now when it is generated, any signal is analog in nature. Okay, and that signal is weak. It is really weak. So there can be noises added to that. That noise is a circuit noise. Okay, it's not the noise you make will be added to that circuit. So we say this noise that are the disturbances. So let's say even if your wires, electrical wires are running in parallel or nearby, they will be disturbance of each other. Magnetic field can disturb, right? The device, some fault in the device can add a noise to that. Even voltage fluctuations can add a noise. So all these are, so to your signal there will be some addition of noise also, and that will, change your signal completely. So the signal is very weak. If when somebody is weak, anybody can come and slap, right? Or anybody can do any mischief. Like that way, if the signal is weak, it is not going to carry the correct information. So we have to make that signal strong. So how do you make the signal strong? If a weak signal is weak and I want to make it strong, how do I make it? Any idea?
Modulation.
Modulation is amplification, amplify, right? You amplify that. You make it 5 times, 10 times more in terms of voltage or current amplifier, voltage amplifier. Are you getting me?
Yes, ma'am.
Yes,
So, yes, so we amplify that. So at the point of generation of the signal, what you need is an analog circuit and amplify karvu pade. You for doing all this, it needs power. See, a circuit is working. Okay, you have components, diode. You must have studied to some extent some transistor, BJT or MOSFET to make this work. To make ourselves work, you have to eat now. If you don't eat, you are weak, you cannot work, you are immobile, right? So to make a circuit work, it will need energy. That energy is given by the battery, the voltage source. Okay, so you will need power circuit. All these power circuits are analog in nature. Okay, and then by time what we have realized is that when you mix, so now by time, as I said, electronics evolved. Okay, so then comes digital. Now what are the advantages of digital? The first thing is processing. If you want to store your data, if you want to process, even if you want to transmit, and it is immune to noise, 0 and 1, right? It is either 0 or 1. In analog, it is from 0 to 1. You will have 0, depends on the precision. If the instrument can measure, it can be any voltage point, 111 also, right? 0.2 point. So an analog, it can take any value. In digital, you have to just handle 0 and 1. Even if the little noise gets added up now, still you can differentiate 0 and 1. So to store, you can store digital 0 and 1, you can store in your memory, right? So storage, processing, all these things are easy in digital circuits. And the resolution, I mean, you can recreate your signal again. Okay, you can store it, you can recreate, and then let's say I am speaking now. Okay, so that goes to the microphone, and then it is amplified, it is stored, and then then it goes, so now it is transmitted, it goes to the server somewhere, right? And then it comes to you. But when you are listening in your loudspeaker, in a speaker, right, it is again analog. So analog ka digital hua, it was stored it can be stored, it can be transmitted, right? And then again it is converted to analog. When you are listening, it is analog. So this is the process. So at the point of generation, then at the receiving end also you have to recreate, you have to make it analog. But digital is for noise immunity, to process and to store. So now you can understand that when you are designing your application, it has both analog circuit and it has digital also. Okay, nothing but they generate some clock frequency signal. Okay, this is how at the point of, so spatially amplifiers. Now there are many kinds of amplifiers, okay, and you may have to have them in stages also. Then for a particular range of a signal, you have to design that, okay, this is the output of the signal, this is the current, this is the voltage or whatever, and then I need a current amplifier, I need a voltage amplifier. An engineer is given a specification, and then you say that, okay, input is this much, output is this much, so my gain should be this much, and now you have to design. Now design means you have to use the component. Even if you are using one transistor to make an amplifier, it is challenging. To design an amplifier with one transistor is more challenging than to design a digital circuit that has thousands of or millions of transistors. You understand that? So now when you are designing something, it will have an analog circuit, it will have a digital circuit. And if your laptop, it will have both analog, it will have power unit, it will have amplifiers. Let's say I'm speaking now, so there's a microphone there. And then as I said, it will amplify, right? All these things it will do, and then it will digitize. There's a loudspeaker also when you are speaking. So there's everything there. So generally in a whole application, the analog circuit is, let's say, 15 to 20% of the total circuit, okay, and digital is 70 to 80%. But the effort to design digital, to design analog, is 80 to 85%. You need people who are good, who has understood good circuits and has an understanding of analog, can only do. Altu faltu nahi kar sakta hai. Even if digital is like, I teach you and you can teach somebody. It's really easy. Everybody will love to do. And it is all on the understanding. If you understand, you love to do. The main thing is you have to understand. Although analog is challenging, but for you guys it is not, because I'm going to explain you in a way that you easily understand. So do you understand now what is analog, what is digital as a whole? And you have studied digital, right? So from inverter to AND gate, NAND gate, NOR gate, all this we are doing. When you design a digital circuit, you can use these blocks directly. Okay, it is like you are having sub-circuits, you drag and drop and you connect and it is almost done. So digital is easy to do it, but analog, even with one transistor, it is challenging. Now in analog, we start with diode. Okay, so are you all understanding, right, whatever I'm speaking?
Yes, ma'am.
Yes, ma'am.
Very good. So we start with diode, and diode, from the name di, means two electrodes, the device that has two electrodes. And it is, basically all of these electronics, diode or transistors, like we are going to study BJT, that you must have studied somewhere in your 11th, 12th, or in your first year. But now you are, as an engineer in this course, you will get involved. Okay, so अभी तक पढ़ा वो कुछ समझ में शायद नहीं आया होगा, and that's why you would have not understood the significance of that. And that critical thinking will only come if some problem is given to you, but if you understand the theory good, you can dig into the problem and try to find out something. So now it's like, you have to digest these things, so that you are better off with handling the solutions for this. So now this diode is basically, so now as I said, in power amplifier, in this power circuits, okay, so as a rectifier we use. Okay, there are many applications. So basically this diode or a transistor, they can be used as a switch on and off But in addition to that, their characteristics means it is the nature of the device. Like we human beings, we have a nature, right? કે ભાઈ આનો સ્વભાવ તો આવો જ છે ને આનો આવો છે. That way, these devices have a nature. They have some characteristics, and that nature is in terms of I and V. You plot I and V, current and voltage graph, and you can understand. Even if you have never seen the device, it will. So, what is I and V? To that device, you give a voltage, and how does it behave in this point? How, what kind of current it passes, right? When you give a voltage. So, this is the nature of the device. And looking to the graph, you can say that okay, this will behave as a switch or a digital circuit, 0 and 1. The same thing can behave as, say, a BJT is a transistor. It has 3 electrodes. It can behave as a switch. It can be used in digital circuits, and it can behave as a, you can make an amplifier. It can be used in analog circuit, but it has some nature. Okay, and that nature also in different, with different voltages, high voltage, low voltage, it behaves differently. So we have to give proper conditions to this circuit for our intended functionality. Okay, and that is known as biasing. કે ભાઈ તમે એને આટલું વોલ્ટેજ આપો તો એ આમ કામ કરશે ને આટલું આપો તો આમ કામ કરશે. So it depends on કે ભાઈ the way you bias, you give the voltages and stuff. So everything we are going to study, and I am going to explain you in an easy way. So basically, and then how it is behaving, it depends on the physics of that. It depends on the physics of the device. Okay, so the material, it is at the end, it is all physics, it is all material science, and they all have equations. So unless and until mathematically, if it is not proven, it cannot be accepted. So all of these things are mathematical. There is I and V equation, which depends on other physical parameters, like the cross section of that. Okay, and the mobility, electrons, the current is because of the electron, because of the hole. So the making of that, and the as I say, the physical properties of that material. So we will see all of those. The current and voltage depends on that, right? So it's that way. And then similarly, these things are for all the devices. There's a physics involved. Based on the physics, you have an equation, right? And then it behaves accordingly. So unless and until we don't prove it, so let's say these are diode, this BJT that you are going to study, right? These are more than 50 years old devices, and they have been used till date. Now, let me tell you, there is something like integrated circuit. You all know what is an integrated circuit?
Yes, ma'am.
Yes.
Yes, sir.
So now in the lab, you must have done in your first year, or I don't know, in your schooling, all this you have seen RLC, resistor, capacitor, inductor, right? And then you have seen diode also. Similarly, the transistor BJT also looks like that. But when you have an integrated circuit, which is there inside your phone or any IC, right? I'll show you everything. I'm just giving you a brief now, the big picture, why you are doing, and you have to understand that. So that IC, the chip, we say, right? It has millions of transistors, and those transistors are known as MOSFET. So transistor is basically a 3-terminal device, okay, which can act as a switch. You can make a digital circuit when I say switch, and you can make an analog circuit also. Now the chip that you see, right, your microprocessor chip, for example, so that is completely digital. Okay, there are chips that have analog also part inside that. Now that chip has millions of transistors, and that transistor is known as MOSFET. Have you heard of MOSFET? Have you heard of MOSFET?
Yes, ma'am.
Yeah, good. See, MOSFET is nothing but it is also a transistor. By BJT means bipolar junction transistor, which we are going to extensively study here. That is also a transistor, but ये जो MOSFET है, it is smaller in size compared to a BJT. Like a resistor, which is a discrete component, and a capacitor, you can have a BJT a discrete one in the lab if you were there, but we will show you through this online the experiments hardware, and also that you are aware of. And so this is like a discrete component, a BJT, like a resistor, like a capacitor, and we perform experiments in the lab. But MOSFET is a little brother of a BJT in sense it is a transistor, but the dimensions is in micrometer. Okay, so micro means 10 raised to minus 6 of meter. You cannot see with your eye. That small is MOSFET. Okay, and now as you can understand, this is really bigger in size. The MOSFET, which is a little brother, and we can make it in an integrated circuit, in an IC, in a silicon wafer. Okay, in a silicon wafer, you can make a MOSFET, a transistor, which is of a scale of micrometer. This is in millimeter BJT. Now you can understand that that guy is really little one, little brother of this, right? And because it is little, now if your home is little, it will have, compared to a mahal, if you are living in a 2-3 BHK apartment, right, it will have lesser area. So similarly here also the size matters. If the size is big, it can have more current. Okay, bigger the size, more current the device will have. We will see everything in detail. I'm just explaining you. So bigger the home, more area. So bigger the device, it can handle more current. So when we compare a MOSFET with a BJT, BJT can handle more current. And more current means your signal is more strong. The signal is more strong means it is very fast, it is very, the resolution wise, because now when the signal is strong, the little noise can do no harm. Your signal is still there, it is as it is. Okay, and then this current will pass through different stages. Okay, in analog also there can be 3 different stages of amplifier, then there can be a filter. Now from the first stage to when it is passing through the first amplifier, it is an input and it goes as an output, and there is another amplifier, right? So your signal should not be attenuated, it should be amplified. So the signal, the stronger the signal, the better. So where you need high voltage, high current, we will use BJT to make an analog circuit. And MOSFET तो क्या है, इतना छोटा है कि it will give in micro range, micro ampere range current देगा. This will give in milli, this will give 1,000 times more current. So where you need high voltage, high current, in applications where you need high voltage, high current, you will have to use BJT. But by time now MOSFET also, there are power MOSFETs available and we can get higher voltages, but still BJTs are more, they give more current and more power compared to a MOSFET. So where you need more high voltage, high power, high current, we will use BJT, and that is used today also in your circuits. Okay, that's what. So this is the very critical part, and for every application you have to design that. And then for running the circuits, you will need to give energy, because if you are working, you are studying good, you are running, you are doing some activity, you will need energy. For that you have to eat. So they need energy. For that we give bias, we give some voltage, that is known as biasing. That also we will see. So there are so many things that has to be done, tuned, very precise tuning has to be done to make sure that, okay, this is my input. Okay, my input, I'm just saying the unit, whatever you want to take. If my input is 1 and I need 10 output, 10 times more, then it has to be very fine tuned in terms of voltage you are giving to the circuit and the parameters of the circuit, the other components we are using, right? Everything. So we'll see all those things. And it is nothing but circuit design, pure circuit design, where you will use your network theorems. You will use Thevenin's, you will use Norton's, you will use KVL, you will use KCL. So my warning to you, or advice or a request, is you please go through those basics of how to solve a circuit. If you cannot do that, right, and then in exam there are like this I just ask is problems, okay, and a question can be 15 marks, 1 5, and then you may lose marks, so you should be good in all of this, okay. Now the amplifier that we design, we need the best amplifier that it should give gain, same gain ever. Whatever things may change, the surroundings, some parameters, voltage fluctuations by time, by aging, it should give the same gain, because like if I'm speaking now and whatever the volume you have said, it should not fluctuate, right? If that is what is, we need consistency. It cannot fluctuate. It cannot give sometimes more gain and sometimes less gain. That should not happen. So we have to make the circuit robust. We do by giving a negative feedback. So these are all, and when you need something very, when you're designing something that is the best, it will add complexity also in the design. But then at the end, it is possible, okay, by putting little more effort in terms of component circuit design, little more power, but you are getting stability. Stability is the main thing. Whether it is circuit or life, people are looking for stability, right? कि भाई ओके शादी हो जाए, then job मिल जाए, so person is stable that way, right? In the circuit also we look for stability in terms of, if it is an amplifier, it is a gain. That gain should remain constant irrespective of any problem surrounding the circuit. Problem means fluctuations that we will see. And then there are other things. Differential amplifiers is, let's say for example, as I gave you in the beginning an example, that a sensor, right, it is sensing something and it is giving the output. If it is sensing temperature, it will give the output in terms of current. By change, if the temperature is changing, the output of the sensor, the current will change, and that current we will then process it, we will digitize it, and then we will have, we'll calibrate it that corresponding to this current, this is the temperature, okay. X current hai to Y temperature hai, Z current hai to A temperature hai, like that way. So that's how things go. So now when you have a sensor, let's say, and a noise gets added to that, right? So the original signal is very weak, and then the noise that is adding is really big compared to that. So kya signal will be like, so it's like now it is all noise only, there is no real signal. So we are engineers, we have found out ways, and we use different kinds of amplifier, that is known as differential amplifier, let's say. So we use different kinds of amplifier to get just the signal, desired signal, and we eliminate the noise and all. So the different kinds of amplifiers here. Another example is a differential amplifier. Okay, and then you have multi-vibrators, where if you are giving an input, a square wave, a rectangular wave, a sine wave, तो वो सब कैसे आता है, right? So there are circuits that make that. When you see a box like thing and you are giving some input, a waveform, sine wave, rectangular wave, right? So all those circuits, they are known as vibrators, multi-vibrators, okay? And you have the lab based on this. So usually pre-COVID time, student used to first do all this in a simulator, LT Spice that you must have used. And then once you do it on LT Spice, you get better understanding. You learn theory, then you do it on LT Spice, and then on hardware. So right, the hardware, how it should behave and why it is behaving. But in this time, this hardware thing, we will show you from the lab. Okay, that Ramesh Bhai, if you know, everybody knows Ramesh Bhai, but if you don't know, you will know him. He has been handling analog lab, and with his help, I am also working from home, but we'll make sure that we show you this hardware-based articles, and what you will perform is an LT Spice. So I have been going on speaking. So do you understand what I said? All of you?
Yes.
Yes, ma'am.
Yes, ma'am. Clearly.
Okay, so this is your
Yes.
textbook. Okay, this is your textbook, and I will tell you what we are going to cover up from that, your textbook. So this is your textbook that I will share, and all this related information I'll update you on our WhatsApp account. And you will start with the diode first. Okay, so the third chapter is the diode thing. And I'll be teaching from that. My slides are also based on this. Few slides here and there may be there. And then at the end, there are exercises. So we'll be doing that way. And this is the reference book. There are more books, but if you do this, is enough too. Okay, and your total weightage out of 100%, 70 is for the exam and 30 for the laboratory, where at the end we will conduct your viva and all. Okay, and so this is how the lectures are based, and BJT is the most heavy part of this course, means more carrying more weightage in terms of lectures and markings. And the point is, this BJT is a transistor, and using transistors we can make analog circuits and digital circuits both. And as I said, this BJT is in few millimeters, right? It's a discrete component that you use in the lab. The smaller brother of this is used in your IC integrated circuit. Integrated circuit itself is like few centimeters by one or 2 centimeters by 1 centimeter, or few mm by few mm, and that has millions and trillions of transistors. And up till date, these circuits were mostly digital. Integrated circuits means they were digital, but in today's date, as I said, the MOSFET also, power MOSFET, we can have analog integrated into that, but still mostly for commercial applications that you see, the analog is a separate, and the digital IC, like your processor, your memory, they are all digital, and it hardly has analog component in that. So analog is a different one. And if you see a board, right, you will have many components and then peripherals, and with your digital IC there. So I will show you that shortly. And this is how. So now whatever, let's say you learn, you are learning this, okay, it will be almost the same thing, but yes, the little different, because the making and the physics also is little different, right? But the overall thing is same, the same goal of using a transistor, whether it is BJT or MOSFETs. If you are good in this, right, then the same principles can be applied to any other emerging device. So now let me talk you from another point of view, that you have seen electronics performance getting better and better, in the sense that you will see your laptop getting more slim and lightweight. Similarly with your phone, right? With, if you pay the same thing, you get better electronics in terms of functionality, in terms of quality, durability, and your battery, and right, even fireproof, waterproof. Am I right or wrong?
Right.
Yeah. So have you ever wondered why? How is that possible? No other technology has influenced this planet Earth like electronics. Why is that possible? Any idea? Have you ever wondered or no? See, your BJT looks like this, like your resistor, the way you do. Can you see all my screen? This is the symbol we will all study. This is how it looks. Had you done something using BGT in the lab ever? अरे हाँ कि ना तो बोलो.
No, ma'am.
No,
Ah,
ma'am.
okay, no problem.
No,
Okay, I
ma'am.
just wanted to know. You all know diode, right? You must have seen this diode. So that way is a BJT of that similar dimensions. But when I say integrated circuit, okay, right, you know this, but this has millions of transistors. Okay, and that transistor is known as MOSFET. Okay, this is how the MOSFET looks, and these dimensions are few micrometer by few micrometer. Now you want to know, so this is how it looks, okay? And it has, so forget this terminal body, it is grounded. It has source, drain, and ground. Okay, it has this three terminal, gate. Source, drain, and gate. It has these three terminals, okay? This is grounded. So this is another transistor which is there in the integrated circuit. So your IC is made up of this transistor, MOSFET I showed you. And that MOSFET is made up in silicon wafer. You must have seen somewhere or other this silicon wafer. Okay. So can you see this silicon wafer, this one?
Yes, ma'am.
Now in that, this
Yes,
one
ma'am.
chip, this one square you see now is your one chip, one processor. It is cut. This is all cut. Okay. And that one chip that comes out is your processor or a microcontroller or a memory or any other ASIC, we say. And this, even this one will have millions of such MOSFET which are in just micrometer range. Now let me explain you how much is micrometer just to get an idea. Okay, micrometer. Uh, uh, okay, let me show you nanometer. That will be good. Okay, so we are here. I just want to show you the idea of how much is 1 micrometer. So see, this is 1 centimeter, okay, and then 1 millimeter. So this ant is few millimeters, less than 1 centimeter, okay. And this human hair is around 100. So 1 micro is 10 raised to minus 6 of meter. So this is centimeter is minus 2 of meter, and micro is minus 6 of meter. Everybody can see, na?
Yes.
Yes, ma'am.
Yes.
Yes, ma'am.
One hair is 10 raised to minus 4 of meter, 100 micrometer. That is the diameter. Okay. And this is even now, if you have to see the tip of your human hair, we will not be able to, right? You cannot see clearly how it is. So that is that. And this is even, this is 100 micro, this is 1 micrometer I'm talking. And the transistors that we make is like 10 by 10 micrometer. Okay. So even less than that. So that, and then these bacteria, and of course viruses are even smaller than the bacteria. So, and this is 1 micrometer, this is 1 nanometer. 1 nanometer is 1,000 times less than 1 micro. This is minus 9. You can see our DNA is minus 8. This atom is in Armstrong. Okay, so this atom. So in 1 Armstrong, right? You can have 2 to 3. In 1 nanometer, you can have few atoms. Okay, so molecules. And in Armstrong, the atom size is in Armstrong. We say 10 raised to minus 10. So we are making the MOSFET that I showed you is of this dimension. It is in this dimension, even less than. So in today's date, we are talking of transistors which are 10 nanometer. So what I explained you is that electronic size is shrinking, and it is getting still better. Every time you get a better electronics, which is less weight and smaller than the previous. If it is same size, you get more functionality. Is that correct?
Yes, ma'am.
Yes, ma'am.
Why?
And
Why we get? If this is the reason that in that wafer, silicon wafer I showed you, in this silicon wafer, so here there are hundreds of chips. If it is a microprocessor, you then it is cut down and there are hundreds of microprocessors you can make from one wafer. This is few inch by few inch, okay, and this may be 1 centimeter by 1 centimeter. Then we package it and we do all this, and you get like this way. So that is then packaged, and then all these connections they come out, because that is in micrometer. You cannot connect it to the external world, and then we have to package it, and these are the connections that come out and you make it. Okay, so if you have Arduino or a Pi, okay, then this chip will fit there and all this will fit, and then it will make connections with the other components. It can be with your any the motherboard or any electronics there, okay, for example. So these are the chips that fits and it will make a connection, as you know. But as I said, the MOSFET that you saw, that electronics is getting smaller and smaller is because of the MOSFET, right? This is how it looks, the MOSFET. It is becoming, it gets smaller and smaller. So the nanometer that I showed you, and there are many such this to see the scale. That one was better. This is also equally good diagram. The clarity is not coming. Nonsense, I think. Now it is good. Okay, so this nanometer, right? Your blood cells, DNA, and then this nanometer. So this is 10, this is let's say 100, this is 1 mm, okay, and then so now that MOSFET, which was in micrometer range from in sub 100 nanometer, is now approaching to less than 10 nanometer. Okay, so it is the transistor MOSFET that I showed you is shrinking. So all the dimensions, they become smaller and smaller. Okay, so every 18 months, we electronics by research, okay, and the way the semiconductor industry is moving, this is reducing in size by half. Area is reducing by half every 18 months. So in the same area, you get double the number of transistors, this MOSFET, because we are shrinking that. And that's why you get lighter, with more functionality and same price the electronics. Do you understand my point? That's why I was showing you, giving you an idea. So now, before it was like, let's say some micrometer by some micrometer, now it is in nanometer. So 10 nanometer by 10 nanometer, even 5 nanometer by 5 nanometer. And now there is a red brick wall. We cannot further miniaturize. If you miniaturize further, there are problems. Are you getting me? Everybody there?
Yes, sir.
Yes, so now there is a red brick wall. We cannot miniaturize this MOSFET further. And we are looking for alternate transistors. And those transistors are known as nano transistors. So if you make this small, then it will not perform the way it should. It is not going to perform, and that's why we cannot go with that. We cannot go ahead with this MOSFET. And we have alternate transistors for the future. They are like single electron transistor. Okay, current is in just nanometer, very low current. But yes, it will give you current of few electrons. The goal is the current with one electron only, final goal. So that small little device in nanometer dimensions, because the device is small, it will give you very low current. Like tunnel FET, CNT, carbon nanotube FET, graphene FET. Okay, FET is field effect transistor, MOSFET. Okay, so BJT is also a transistor. So that's what. So the future is emerging transistors, nano transistors that will make your circuits, and it will have properties that you cannot even think today. It has no counterpart in today's technology. They are like magic. Okay, so that's the goal. And now I hope you understand why do you study this analog. And analog is the base of digital. If you know analog, digital is not a big deal. But anybody who knows digital may be still zero in analog, and analog engineers are highly paid. And it is hard to find, even if you can count on your fingertips, good analog people, right, who have good knowledge of analog design in the whole country in your fingertips. It is even, you will not find this course even taught at many good institutions because they don't have professors who can teach analog. Digital, I can, even a student can teach once he has done. So that is the significance and importance of analog circuit. It's the base of digital. So that is all about analog. And this is how the lectures will be there. And the lab, you all have same day lab. Everybody has same day lab.
Provided with the timetable.
Yes, timetable.
On which day it will be?
So I mean that updated timetable you have not got. That's what you are saying me, right?
Yes.
Yes, sir.
Yeah, because if you have to make it to the class, then it was like different batches. But I think in one day only you will have all together only, but the TS will be there and we will be also there. The other batch is taken by Professor Nalin. So the thing is you will maintain a lab book, okay, and you will perform in LT Spice. You all have downloaded.
Yes.
Yes.
Yeah.
Okay. So now in the next lecture, my first lecture, what I'm going to teach you is this. Okay, we start with semiconductor physics, and that's the base because your BJT, your diode, or the MOSFET, whatever electronics we are talking, most of the electronic, okay, in the commercial electronics, whatever we are using, they are semiconductor. Now, who will tell me why? What do you mean by semiconductor, and why are these electronics semiconductor in nature? समझाइए हमारा सवाल. You understand my question? This diode is semiconductor. That BJT is a semiconductor. Even MOSFET is a semiconductor. So why are this electronics semiconductor in nature? See, I feel that you are all intelligent little Einstein, but you have to behave like that way and you have to reply me sometimes out of your knowledge, whatever you studied or you know. It's all logical.
Because we can control the flow of voltage and current in semiconductor.
See, flow is of current. Okay, voltage ka flow nahi hota.
Current. Not.
So you want to control. So with conductor you cannot control, you mean?
No, means ma'am, conductor does not provide much resistance, but semiconductors are material that provide resistance so that we can minimum flow of current, control flow of current
Okay,
we can
yes,
pass.
yes, good, good. Correct. See, main thing is control. Insulator we have to forget, right? We don't get current at all or very low current, and that cannot work because this current is the one that is, it is like a river, okay, that is flowing through various cities. So current is like it is flowing through various stages of the circuit, right? And when a river is flowing, if it is starting from Himalayas and if it is flowing, then we will wish that it will deliver water to throughout where it is flowing, right? It should not be like after 1,000 kilometer or meter that water should be exhausted. ऐसा नहीं होना चाहिए. River, everybody should get the water now. Similarly, here also in the circuits, when your current is flowing, which is carrying your information from one circuit to other, right? That equal strength of signal should flow. It should not die out. Your current should not, otherwise your signal is lost. Whatever information it is carrying, it is lost before it comes to an end. So for example, if I'm speaking from here and you are listening there, then at all the stages your current, it should come to your system, and then from digital it should be converted to analog, and there also there should be an amplifier, and then it should come to the loudspeaker, okay. But in between only, if it dies out, then you will not have a signal that is reproduced, okay. Forget here, if I am talking in the class, then also, right? Or I mean, here it is all different stages, it is going through the cloud and all. But if that is not the thing, and if I'm speaking in the class, then also it should, that from the loudspeaker, I'm speaking in the microphone in the class, and it should come up with equal strength in the loudspeaker. It should not die out in between, right? That's the goal. So your signal should be so that insulator will not at all work. Now semiconductor and conductor. In semiconductor, main thing is control. You can control very precisely. In let's say if it is a conductor, then on किया off किया उसमें कुछ control नहीं रहेगा. Even little fluctuations will make it on or off. In semiconductor you can control, and what is the control? That a voltage, or you can control because of the voltage the current. Okay, so very precisely that by giving, the current is created because you are giving a voltage. Voltage is nothing but What are it? Voltage is, what is voltage? You are giving a voltage means you are giving some potential, and that potential is because of the negative and positive carriers which will flow eventually. Okay, so if you recall, and we will see the physics, the band gap. There is a valence band, there is a conduction band, and the electrons, they move from valence band to conduction band so that you get a current. And then it should not be that you have to give very high voltage also, right? Then for little current giving too much energy, we are human beings, we are intelligent people on the planet, we want more output, like you are investing less and you are getting more return. That's what we want. So with little voltage we want more current, but that control has to be there, that I am giving this much voltage, then I get ऐसा नहीं कि थोड़ा कुछ भी fluctuation है और वो शुरू ही हो जाए. So that control is main thing. So and then that's what you get in semiconductor, as he rightly said. And then this is the base of your circuits. Semiconductor physics on which your diode is based. We'll see many circuits of the diode, and then that's how the BJT is also based on that. Right? And MOSFET is not there in your syllabus, but all these different circuits using BJT. And it's tomorrow, let's say you are planning to study further your master's or PhD, then VLSI, that is your circuit design. Even we have masters in our institute in VLSI. And then the future is nanoelectronics, in which I have done my PhD. Okay, so if this is strong, then you can do that very easily. And if you are studying VLSI or doing or studying nano, then it's all interdisciplinary. You have physics and then mathematics, of course, because you are deriving the equations. And if it is not supported by an equation or a mathematics, right, then that will not make it as a device. You cannot commercialize it. You cannot make a circuit, because before making a circuit, we have to simulate it. And these equations are the base. If you don't understand, if you cannot make an equation, it means you have not understood the physics. So physics is the main thing, then mathematics, the equations of that, and material science. It's all semiconductor, as we have to understand the semiconductor physics here. So it is a material science, then your simulator, because if you don't have a simulator, then you cannot see making a circuit directly is expensive. Especially integrated circuit. If you want to have a one chip, it cannot, because it is, as you can see, your one transistor is in micrometer range, in less than micrometer, and you are making millions of that. So you need a very strong computerized tool, which will mimic your real circuit, and that is known as simulator. So all the simulations, then how to make a circuit. Now, when you make a circuit, there are different devices. You have forget emerging device, but you will have, if I'm talking of now present technology, and forget MOSFET, also integrated circuit. If you are making just with the BJT, you will have a BJT. You may have a diode if the circuit needs, but in addition to BJT, you will have R and C. So many things come, and the simulator should be able to simulate, and it should, like your real circuit, it should be able to mimic it. So if you don't have a simulator, then directly going and doing, see, an engineer's job is not to go in the lab and to connect to connections, not connect and then give a voltage and see. The engineer job is pen and paper work. That any diploma can also go and do, or little knowledge, and you tell, okay, jaake dekh lo simulation karke. So it's all design principles, the theory, the circuit design. As I said, you should know all this, how to do that. So that is a job of an engineer, and it is very logical. Yes, you have to be good, but that confidence or being good in the subject only comes out of hard work. because we all are intelligent, not we, at least you all are, forget me. I believe that you are all little Einstein, but your goal has to be focused. And this seems to be the same thing that you must be knowing since you are young and you are, on your own. But believe me, this is the only key to do good in something that may seem to be challenging, because पीछे पड़ जाना है तुमको if you don't understand, and I am there at every step. Okay, so I think I have given enough and spoken enough. Anybody has any query, you can type in the chat box or you can unmute your microphone and ask me.
Ma'am,
Bolo.
ma'am, as you said, we can double the number of transistors on a specific chip uh, as
Yes,
compared to 18 months ago. So uh,
yes, you are right.
that was some rule or law
Yes,
made by
it is
some
known as
person,
Moore's law. That law is
and
known as Moore's law, Joe. I'll show you. Okay, so this is, it is not, this is, it is a prediction. Okay, you can say it is a prediction. It is known as Moore's law, and that's how the semiconductor industry, it follows this. Okay, this is more than 50 years old law. Okay, Richard Feynman, he had given a lecture, and this is by Golden Moore. He was a co-founder of Intel. Okay, so Moore's law on Wikipedia also it is that he was a Golden Moore gave this, and he was a co-founder of Intel. And you can see this is up to 2020, right? And the transistor count and year wise. So it has followed this. So it is a prediction that the semiconductor industries, the academia, when they do research, everybody follows this, and that has been followed since more than 50 years. But now, as I said, there's a dead end, there's a red brick wall, and we are human beings, we need better and better. It's not that, okay, for our use, as far as TV and your laptop and phone is there, if you don't get a better version, it's okay. We are not using what we get today also. But if you want to make it to another planet, because we are all, it is okay, our planet is beautiful, and of course once we in our home we may feel like a jail, okay, but we are confined on the planet Earth, okay, as a human race. કોઈ meteorite આવીને પડે તો we have to find an alternate on another planet or whatever other bodies, right? So for that you need a technology, okay, and only technology can save us. કે ભાઈ માસ ઉપર જઈને કરું, માસ ઉપર પહેલા તો પહોંચવું હોય, કે interplanetary mission you want to do, or you want to have, right? As a human race we want to conquer universe, forget our planet. So only technology can help. It's not that for talking on the phone we need a better technology, right? And then, as you know, this all war, like why America is powerful, it has weapons. Latest ek chap dabawe, the whole world will get destroyed. So the one who has this technology for all these different kind of applications, they are ruling the world. So India so if you want to have a mission to a Mars and establish a colony, to શું જોવે આપણે? Technology જોવે. If you can do that, India is ahead of America also. So the technology will put you ahead. Space ઉપર જવું હોય તો, એક elevator બનાવવું હોય તો space ઉપર you need a technology. So this is what you are right. So this is Moore's law, and we have been following, and you know how we as a human being, the way electronics has progressed. So it has
so
been
ma'am, my question is, this Moore's law is applicable only on MOSFETs or all types of transistors?
Okay, good question. It is applicable to MOSFET only. કારણ કે જેટલી IC છે, જેટલી chip છે, is all made up of MOSFET. There's nothing else inside. It's like human body is made up of cell. Your IC is made up of MOSFET. Emma, if you want, a resistor is also made up of MOSFET, let's say. So IC means
Okay, ma'am.
MOSFET, nothing else. 100% MOSFET, MOSFET, MOSFET.
Okay, thank you, ma'am.
Okay, good question. Anybody else? Okay, then we'll meet on Friday and I'll start with the first lecture, semiconductor physics.